All right, welcome everyone. I am Peter Sadowski, an assistant professor in information and computer science. I also have Katie and Mingyu here, and we're going to be presenting machine learning for climate science. So I'm going to start off by giving a brief overview of what we're going to be talking about.
Recording in progress.
So the outline of the talk is here on the CI Tracks GitHub webpage. This link up here. I assume everybody has that, but somebody can post it in the chat if somebody does not have it. And what we're going to be talking about is how to apply machine learning to some common problems in climate science. So machine learning is increasingly important for modeling all sorts of data, including climate science data. And I want to introduce two general themes of how machine learning is being used. And then we're going to go through a tutorial of and actually see the code of how you would do it in each of these cases. So the two common themes are downscaling and emulation. So downscaling is this idea that you can take some simulation of weather or climate and use machine learning to make more accurate predictions at a very fine local scale. So the way we predict the future climates and the way we predict future weather is to basically take the whole globe, characterize the climate and weather variables at different locations around Earth, and then run through this big physics simulation of how that system evolves over time. Discretizing time and space and stepping through the physics of how the system evolves. So obviously, we have to make a bunch of crude approximations when we do this. And we're basically limited by the size of our largest supercomputers in the resolution and accuracy of these methods. So the idea of downscaling is to turn these crude forecasts of future weather and climate into a more high resolution forecast that we can use at specific locations. So there's two different types of downscaling. There's dynamical downscaling and statistical downscaling. Dynamical downscaling involves running a physics model for a local area that matches the constraints of these larger models. We're not going to talk about that today. That's, it requires expertise in atmospheric sciences and climate science, and that's beyond the scope of this workshop. But we can talk about statistical downscaling, which is where machine learning comes in. And the basic idea here is we take as input these crude forecasts, and we predict what that means for a very specific location. So I know this is a workshop on climate science, but I'm heavily invested in AI weather forecasts right now because I'm competing in this competition, and it's basically the same idea. So I wanted to share this quick example of how this can be used, and it's similar to other advanced examples in climate science. So the way we do weather forecasts is NOAA runs these big simulations on supercomputers, and they release these simulations every 6 hours, which predict the weather variables basically a week out. And all the weather forecasts you get online come from these simulations run by the government. But the simulations are very crude in that, you know, one pixel covers a huge area of land, like the entire island. I didn't need to go there. So we have one pixel prediction for every hour in the next, 10 days of what the weather will be over the island of Oahu. But that's not particularly useful for us if we care about the weather here in Manoa, because the weather here in Manoa is not necessarily what the entire island sees. So the way we deal with this is we can take machine learning algorithms that predict the weather here in Manoa from the forecast for the entire island. And that's what I've done here on the bottom for a site at Kona. And what I'm doing is I'm predicting for every hour of the day, I'm outputting a distribution over what I believe will be the amount of sun hitting this particular location at the National Energy Lab at Kona by the airport. So when the forecast says that it's going to be somewhat cloudy over the island of Hawaii, the Big Island, my machine learning model says that at this specific site, we can expect this level of clouds and this level of, so this is a radiance on the y-axis here, the watts per meter squared. So this is we train this machine learning model based on historical data, historical predictions versus historical observations. Those are the inputs and outputs of the model. And then we can use that to forecast the amount of sun that will be available in Kona tomorrow. So in climate science, we just kind of scale this up to months, years, decades, but we can do the same thing to predict how much rain the islands will get in the future. Okay, the second approach that we can use machine learning for in climate science is emulation. And this is the idea that you do a crude approximation of these really expensive simulations with machine learning. So these simulations try to model all the physics that goes into weather and climate over the entire globe, and they have to be run on supercomputers. But machine learning is really good at approximating functions. Physics is just a function of the current state of the atmosphere and the output being what's going to happen next. And you can train a machine learning model where the input is historical information and the output is what's going to happen in the future. So there's a lot of interest right now in using big neural network models that take in all the historical data and predict what's going to happen in the future. And what that gives you is a fast way of running these simulations. They may not be exact because they're not based on physics, but if they approximate the physics good enough, then you can get forecasts with very low computational cost. So one advantage of being able to do these fast emulations of physics is you can perturb the initial conditions, run the simulation, your fast approximation to the simulation many times, and that gives you uncertainty bounds on what the future weather or what the future climate will be. Okay, so that's kind of the overview of the two different approaches that are being widely used in climate science. And we're going to go through some examples of this. But before we do, does anybody have any questions? All right. So I'm going to turn it over to Katie next. And Katie and Mingyu are going to talk about a downscaling example. But really quick, for the second part, we're going to do an emulation of a climate simulation. And the data set's a little big. It's like 120 megabytes. So if you want to start downloading that now, that might be good. Just as a, it might save a little time later. And the second Colab notebook, you'll have to upload this to that second Colab notebook. So this really only affects you if you're at home and you don't have a fast internet connection. But yeah. All right, Katie. Online.
Hi, I'm Katie. This is Mingyu. We're both part of the Department of Atmospheric Sciences, and we are by no means computer scientists, but this is our best attempt at being able to deliver you a machine learning model that's going to help you with time series. So time series are obviously super important in the context of climate, but they can be used for tons of other things, like Peter was saying he's doing the solar irradiance, or basically just how much sun is coming into the earth. That's a time series. We have tons of time-dependent things, and so hopefully you can find a use for the code that we're going to provide you in your own research if you work with time data. So while we're waiting, if everyone can go to the link, does everyone have the link that isn't necessarily on Zoom or knows where to get it? Basically, that's the site that he was showing you with the, I don't know how to make it like shareable to everyone in the room who's not on Zoom. Maybe I can put the link up there when we're done. We'll have you go to that site, and there's going to be a little box that says open in Colab, and then you're all going to open in Colab, and it's going to show you like basically our demonstration. Cool. There we go. So if everyone could go to this link on Zoom as well.
Sorry.
For some reason, they're saying that they can't get to ours either. Oh no. UH emails shouldn't block Colab, but they've been doing weird things with.
Oh yeah. You can't use UH Gmail to access Colab.
Okay, so I hope everyone heard that. You can't use your Google email to get the Colab, which is.
You need a separate.
And Maddie's saying if you open it up in incognito mode, then it works. So hopefully that in incognito mode or private mode.
Sure.
Well, thank you, Maddie. Okay, so it's going to bring you to this site. Mingyu, do you want to come over here? Yeah, we're going to talk a little bit about what climate science is and the intrinsic variable or the barriers that climate science has. Do I want to unmute me?
No.
Okay.
I made that mistake.
Okay.
Okay, so today our topic is machine learning approaches in climate science. So first of all, you may ask me, what is climate science and what is the differences between climate and weather? Because these are two words we usually heard, but we don't know what the difference is between them.
Yeah, okay.
Um, briefly, summarize them. Climate is the long-term consideration and weather is a short-term consideration. This means that we have different weathers every day. Maybe today we have rainfall and tomorrow is sunshine. But climate, we usually consider whether we will have more precipitation in the future, something like that. So this is the differences between weather and climate. And you may ask me, why should we consider about climate? We all know that we consider about whether it is going to rain today or tomorrow. But the reason why we should consider climate is that climate can change the static atmospheric condition. And so we should care about it, especially under the global warming. So first of all, we have many obstacles to climate predictions. The first kind of obstacle is the neutral climate oscillations. I think the first type of oscillation is the relationship between the Earth and the Sun. Here I have an example of the Milankovitch cycles. This is a very long-term cycle, and we usually have another one you may be more familiar with is the seasonal cycle. It's usually the relationship between the Earth and the Sun. And others, we also have other kind of climate oscillations based on our atmosphere and the ocean. And here I list 10 neutral climate oscillations. We may have a very interesting thing is that even the El Nino Southern Oscillation and the Pacific Decadal Oscillation, they're all over the Pacific. They have very different time scales. For example, UNSO usually have the time cycle between 5 to 7 years, but the Pacific Decadal Oscillation, from its name, we already know that it is a kind of decadal cycle. So this brings us the difficulty to predict climate is that if we have unusual cold summer, it's hard for us to determine whether which kind of oscillation is the main mechanism to cause this unusual system. So here we have different kind of neutral oscillations, but our human can also impact our climate to a great extent. Under the global warming, we just say that the human activity can also alter our climate as well. Here, this figure shows the temperature change in the last 50 years. There are two interesting phenomena in this figure. First of all, we can see the air temperature increases much larger on the land, over the land than over the ocean. And second one, the Arctic. The air temperature over the Arctic increased rapidly at a rate more than twice of the rate of the global mean. Generally speaking, the global temperature all increased very rapidly in the past 50 years. But you may say that okay, it's the temperature increases 1 or 2 Celsius degree, but we can also survive because we have air condition. So why should we still care about that? I would say that the air temperature is only a representation of the climate change. But the air temperature increases can also totally change the atmospheric static condition, which means that we may have different rate of heavy rainfall and droughts. In this figure, I show that the observed precipitation change in US, we can see different areas have different changes. In the southwest US, we can see there are much more droughts. Even they can cause much more wildfires. And in the northeast US, we can see there are much more extreme precipitations. So in this way, we can see that the global warming cannot only cause the temperature change, but can also change many weather disasters. So let's go back to our workshop. And what can we do in this workshop is to use the machine learning to help us better predict the climate. Here we select the very famous oscillation named ENSO. ENSO is also the El Nino Southern Oscillation. It is a term used to characterize the warm and cool phases of the tropical Pacific Ocean, especially the middle to East Pacific. And El Nino was the warm phase of ENSO. It was first noticed at the periods of unusual warm water in the Pacific Ocean by South American fishermen. Here I have some figures to show the mechanisms. We can see the El Nino phase, we have very warm water here. If you're more interested in the mechanism, you can read it. But here I want to more focus on the impact of ENSO. Here, we compare the normal phase and the El Nino events. We can see the warm water here in El Nino is caused by the weak upwelling in the ocean. But the upwelling here cannot only cool the sea surface, but can also bring nutrition from the deeper ocean to feed the local plankton and fish here. So during the El Nino events, if we have much weaker upwelling, it can bring far less nutrition here to feed the plankton and the fish. So even the birds on land may not have enough food to survive. In this way, we can see that El Nino can impact, even though El Nino is a phenomenon in the atmosphere and ocean, it can also impact on marine ecology to a great extent. So this is the first story of El Nino's impact. And the second story is that there is a very interesting phenomenon in the atmosphere called teleconnection, which means that even a local forcing can cause a global impact. This is also called the butterfly effect. In this way, we have normally sea surface temperature in the Eastern Pacific during El Nino and La Nina phase, but we can see different areas on the Earth have different reactions to that. Many places have droughts, many places have floods. So this is why we should care about them. You may ask me why there is very strong teleconnections. I will say that even the ocean has different basins, but there is no basin in the atmosphere. So the atmosphere is very flexible and light. It can travel very far. It can travel to everywhere they like. So this causes that the climate oscillation very, very important. Even though it is only a phenomenon in the Eastern Pacific, it can cause a global impact effect. All of these, both of the stories here shows that the ENSO have great impact on our global society. So how do we? But nowadays we still don't have great method to well predict El Nino. So so here I will list some of the limitations of our current method here. And maybe we can use machine learning to better predict ENSO. Mostly we use the numerical climate model to predict ENSO. It is a set of closed equations in which each equation is the physical hypothesis constructed by climatologists through their understanding of the climate system and expressed by mathematical equations. But we know that they are all based on what we have understood. But there are also other key processes that we haven't understood, but they are very crucial for the prediction. So many scientists believe that the main reason for the defective model is the lack of simulation of the actual detailed physical processes, which is not included in the large-scale atmospheric and marine dynamic framework used in the current climate models. The key problem is that the grid box in the climate model is too large. The length of the grid box is usually more than 100 kilometers, which means that we have too coarse horizontal resolution and cannot capture Hawaiian Islands. It is like we have a very coarse net, so we cannot catch any fish. We don't know what actually happened inside the gray box. However, this kind of small scale simulation are so important that some of them is the key to improve the large scale answer prediction. So the downscaling is crucial, but very challenging task. What is downscaling is just introduced by Peter. And today we also have more and more local observational data sets, but our climate models are still not able to directly take advantage of them. So if we can use machine learning to complete these local simulations and at different places, we believe that it will largely improve the simulation and the prediction ability of the climate models. So here we want to help improve the prediction of ENSO. We think it's very necessary to build a machine learning model on time series for the sea surface temperature of many different local spatial points in the Pacific. To make our case simpler, we just select one spatial point as an example. It is located between the middle and the east of the equator in Pacific. And it is also one of the regions with the worst climate numerical simulation. We hope to get a mathematical method from machine learning that can accurately simulate the temporal sea surface temperature at this spatial point, so to improve the prediction of ENSO in the future. And next part, we want to introduce about machine learning, and I will give it to Katie.
Yeah, I don't know why it's repeated. It's just like whole grid boxes. Okay. Sorry, I don't know why this is on here twice. Okay, but if you scroll down to using a long-term, short-term memory model for climate time series. Well, first, thank you, Mingyue, for summarizing a really complex phenomena in atmospheric science. Hopefully, you all kind of understand why we care about ENSO. It's got a lot of global impacts, and right now it's currently one of the most difficult things to predict in future climate predictions. A lot of this comes from the fact that we really just lack observational data. We've been collecting data in the atmosphere for about 100 years, but it's not necessarily controlled or accurate. And we don't really have 100 years worth of data on a global scale. And in the ocean covers 3/4 of the globe, and we have maybe 30 years of data. A lot of the climate oscillations that we had mentioned in that list above, they can be anywhere from a couple years to a couple months to decades. And it's really difficult with limited observations to decouple how all of these are influencing one another. And it also creates a problem for us when we're doing machine learning. Like machine learning really likes when you have nice patterns, it makes it easier to learn things. But when you add variability like human impacts that are going to increase the global temperatures without a necessary or without like an obvious forcing to the machine learning model, it's difficult to train on those types of things. So anyway, here we are definitely not solving the ENSO problem. We just wanted to establish that this is something that we hope that machine learning will accelerate our understanding of, but and use it as an example in this specific model. Cool. Okay, so the first step to this, and you should all be able to run all of this code in real time. Also, if you wouldn't mind now, I should have said this in the beginning, but file and saving the notebook as in your own drive. That way, I think we aren't editing all the same notebook. Yes. So anyway, if you could do that now, or maybe you can watch me do it in real time.
I don't think it will let them edit it. They can view your notebook, but they can't run it.
Oh, okay. Well, then I'd like you all to be able to copy it so that you can like run it on your own computers, and then you have it forever. Hopefully, it will be useful for you for your own types of stuff. So I'm basically going to walk through not every line of code. Hopefully, you have some familiarity with Python, but we're going to be using Python's a little bit of sklearn and some Keras, which is a deep learning package. Package is not the correct term, but okay, deep learning package. And something called a long short-term memory model. So just as an overview, a long short-term memory model is something that's able to take previous time steps worth of data and use that as a consideration for the future, which is what we would want to do in a time series prediction. We'd want to say, given X number of time steps previously, what is the next time step going to be, or what is the time step going to be in the future beyond just one time step. So we'll import, oh, guess I should do this here too. I apologize. This is the first time we're doing it in person. Okay, so we're going to import everything. Everything should already be there for you. Hopefully it just initializes the notebook and runs with no problems. Using Google Colab is really nice because it has TensorFlow as a backend, which is required to run Keras. And if you wanted to do that on your own computer, I know right now, if you have one of the new Apple computers, the M1 chips struggle with TensorFlow. There's some like weird things that were happening when it first came out because the M1 chip is a neural network in and of itself. And so if you're not completely computer savvy, it might be worth looking into using Google Colab if you wanted to use TensorFlow as a backend. But yes, anyway, moving forward, we have our data set, which is right there on GitHub, and the data set is approximately 30 years worth of sea surface temperature at that location that Ingrid mentioned, which is 0 degrees north or right at the equator and 140 degrees west. This is going to be right within the El Nino 3.4 index, which is basically a region of the ocean that they use to determine whether or not we're in a period of El Nino or La Nina or neutral. So we have observations from a buoy system that was put there 30 years ago. And initially, we're just going to plot the data and we're going to see what we're working with. So this is daily timescale data. And as you can see from the missing dates below, we have missing data, which can be a problem because if you don't have a continuous time series, that means that your model might be interpreting the next time step, which is potentially years away, as the next actual time step within the model. It might be assuming it's the next day as opposed to years away. So there's a couple ways that we can fix this. Obviously, you can either just choose to ignore it, or you can resample it, or you can fill it in with some kind of like interpolation method. So here we have you create just a couple different data frames just for the use of this model below. So this is just a simple forward fill method for the dates that are currently available. So we have this weird forward fill method. It doesn't do a particularly good job, but now you have dates. There is data there. It's not necessarily correct data, but there's data there nonetheless. And then you can also do monthly data. And so for monthly, we've regrouped it to monthly stuff. And now we plot it for a month. I will say that monthly data is probably more important with regards to ENSO because that is how we that's how we classify ENSO, is based on monthly sea surface temperatures. However, when you're thinking about a climatic timescale and you only have 30 years worth of data and then you only have 12 months, you only have 360 data points, which is basically nothing for a machine learning model to learn off of. So these are all things that are really important to consider when you're resampling your data, but are all of the, is all of the variety that you experience on a daily timescale, is all of that necessary or is it noise? Here you could apply like some kind of smoothing function or whatever. There's tons and tons of ways that you can process climate data. You could put it into Fourier space as opposed to actual space. But anyway, so moving forward, I'm going to like break down what an LSTM model sort of is and how this code that we have written works. There's tons of other ways to do LSTM models. That's like the uniqueness of machine learning, is that you can, well, of coding in general, is there's so many ways to do what you want. But this is just a way that I have used in the past and found to work. So beyond this, you'll see that there is this function called series to supervised. And basically what this function does is it takes your data. So we have air temperature and sea surface temperature, and we're going to try to use air temperature and sea surface temperature to predict future sea surface temperatures. And it creates different columns for previous time steps based on however many time steps you decided matter. So if we said that the previous 3 days matter, we would put that into this series and supervised function, and then it would create separate columns that are now lagged. So for day 1, you have this air temperature, and then you have this air temperature of the previous day, you have the air temperature of 2 days before that, and you have air temperature for 3 days before that. And it creates these columns that just become extra variables, essentially, for the machine learning model to learn off of. Again, there's like other ways to do this, but I found this function was useful and kind of a neat way to approach this problem. So you'll just run that, it will be defined. And then here is all of the code you needed to run a machine learning model in one go. So I'm going to walk through some of the lines that I think are like particularly important. And then you'll be able to run all 3 of the data frames that we created above, the one with just the regular data that it's still missing values, the one with the forward filled data, and then the monthly data. And it's going to print out the root means absolute error of the model. And yeah, and it's going to show you how your model does compared to actual observations. So the model function, it takes in a data frame, whatever data frame you have. It takes in a name, which is just whatever you would like to title your model. And then it takes in the number of days or number of time steps that you'd like to lag something by. And then the number of features is just the number of variables you're considering. So then it's going to ask you how you'd like, and you'll see down in the code below, it will physically ask you how many time steps you'd like to train your data on. Typically, when you're training a model, you want to do 70% of train and then test on 30% of your data. And so given, it'll show you the length of your data set, and then you can choose kind of arbitrarily what you think 70% of that is, or you can calculate it exactly. And if you decide not to enter a realistic value, it's going to train on 70% anyway. Then what we want to do in this part right here is we're going to scale the data. So we want to take the data and basically scale it from 0 to 1. And that's going to just make it easier for the model to train on. I don't know why, but that's what I've been told to do. And so that's what you should do as well. And then after that, we're going to create our series supervised function. So it's going to take our scaled data set and then the number of days that we specified we wanted it to time lag on. And it's going to create this new reframed data set with all of those lagged days as new columns. Then we're going to separate it into our training test and testing set. Again, all of this is literally just done in the code. And we're going to reshape them. And basically what we're going to do here is we're taking all of the columns for what we want to be trained on. And then this one is going to be the final column, which for us is sea surface temperature at its current state. And we're going to, like, that's going to be the y, basically. Like that's this, the first part is the x and this is the y. This is going to be our output that we want to get. We'll do the same thing for the test. We're reshaping the data, which all of this should do as long as you put in those correct features above. And then here we get to the actual model. So we're going to do a sequential model, and then we're going to add the LSTM description of it. This is going to be 50 epochs, which is just the number of iterations that you want the model to go over. And you're going to define the input shapes of what you're going to train on. you can play around with all of these parameters like dense and there's dropout and all of these hyperparameters that are beyond my area of expertise, but this at least will allow you to get the model going. Then you're going to compile it. Our loss is going to be mean absolute error, which is May, and then we're going to create our model. So here is the model code. Basically, we're just going to validate it on the test set, and we're going to train it on the train set. And then we're going to plot all of that for us so that we can see how the model is converging. After that, we're going to unscale all of that data and predict using our test set of x's, and then plot that to see how our model actually performs. So cool, yeah, hopefully if you run this, it should run with no problems. And then here in this first function, so we're saying this is going to be our daily unprocessed. It's just all of the sea surface temperature, but we decided not to use any forward fill or anything related to that. We're going to train on 30 previous days because why not? You can train it on whatever you'd like and your own thing. And we have two features. We have sea surface temperature and we have air temperature. So hopefully this runs. Oh, it's going to ask you how many time steps you want to train on. So there's 8,000 in this one. So let's say 5,800 is 70. And now it's going to go through all of the training. And hopefully it does well. So the reason that I like this code is the way it is because in order to create a good machine learning model, you have to go through several iterations of this over and over again to test how your model does when you put different types of data in or different processed data in. And I wanted code that would be nice and optimized your ability to do so that you didn't have to spend lots of time fiddling around with the model stuff initially to find the best data set.
So how many time steps are input to this one?
The outbox?
How many time steps of the data?
5,800 time steps. You mean what? How big is the training set?
No. The number of past time steps that you use to make.
Oh, 30.
30.
Yeah.
Okay.
Yeah, we used 30 days in this. And even though this function says n days, like obviously if you were looking at months, then. So sort of interesting. But this is our overall loss, which is like not the worst. So it does like an okay job. I actually think this is running off of the previous or the processed data. I don't know why, because they're named different things, but it could be just an error from above. And then you can do the same thing with these, which have longer time steps. So this would be like 7,000. And then the last one is months, the monthly data. And if I wanted to train it on 12 months, so a whole year's worth of monthly data previously, then you would run this code as well. And then once you get past all of this stuff, this is basically how the monthly does, because Google Colab keeps everything in there. So this is the model predictions versus the actual observations. You can see that it doesn't get the peaks as well as it should, but that's to be anticipated. Models typically aren't good at looking at outliers or anomalous events. And there is a bit of a lag for some of this prediction, which is interesting.
So that's because the model tends to predict what it saw last, right? So it's like a persistence model. If it's a certain temperature this month, it predicts it's going to be a similar temperature the next month. And so that's why it's kind of predicting the same thing. And so in the plot, it appears as a lag.
It's less apparent in the daily data. And it might be something you would want to consider for the daily data and then resampling the daily data to monthly data to get future predictions. And then model tuning is something that I'm still very much learning, but I have provided some interesting resources for you on how to tune different type of parameters within the Keras time series, the Lstm example. But yes, hopefully this code is like a nice jumping point for you, and you can use that entire function above and your own CSV file in order to see how well it does with different types of time series predictions. And I'm also really happy to chat about any other types of time series predictions people have done, and if there are better methods than the series to supervised function that we're using here. Yeah, that's basically all from us. And now it's back to Dr. Sadowski.
All right. Any questions on that before we move on to the next one? All right, so I'm going to switch over to the second Colab link, which is a similar problem. We're predicting sea surface temperature, but now we're going to do it on a global scale. And this is going to demonstrate how to deal with time series data of images instead of just variables. And it requires significantly more engineering backend. And so I wanted to demonstrate how to do that in Keras and TensorFlow. So in order to run this, you need to download these two files. The second file is 1,000 years of climate simulation run by a Canadian research group. So it's monthly data over the entire globe at 1 latitude, longitude, pixels, and it's monthly over 1,000 years. So 12,000 samples. And then this dataset file is basically just helper functions that helps you process the data into a machine learning ready form. And that becomes super important for these big machine learning models. So basically any machine learning project, all the work can be broken down into 3 parts. There's the data sourcing and preparation. There's the data modeling part, and then there's the deployment. So here we're focusing on the data processing and sourcing, which is usually most of the work, and it's really hard to automate that because you really have to understand the data and be familiar with your data. The data modeling part usually involves training a bunch of models over and over again and fitting all these parameters. So we're kind of skipping over that part here. We're just showing you one example of a model that works, and you can fiddle with it yourself. And then here's a link to a paper where this project and code came from to give you a little more background. Okay, so what we're going to do here is we're going to take in, let's see, a couple months worth of sea surface temperature data over the entire globe, and we're going to predict the next month. So what Katie and Minghui showed was how to do this at a specific location. Now we're going to do it on a global scale. So you can run this cell to get started. Actually, pro tip, we're going to go to runtime and change the runtime to a GPU in order to make use of GPU acceleration. And when I change the runtime, it's actually going to switch the machine I'm running on, so it has to restart the kernel. Okay, yeah, so in order to upload these files, I'm going to have to I have to download this file real quick. Sorry. Have most people managed to upload these files? Okay, here we go. It's kind of big because it's 1,000 years of global simulations. Okay, so I'll explain what's going on here while it's uploading. So this dataset file, if you want to use a big neural network for your own project, you are almost guaranteed to spend most of your time building the data processing pipeline to feed the neural network. So, this is a data engineering component of your project. So I'm going to put this over here. So, the whole purpose of this file is to load in this data set and create a generator object which feeds batches of images to the network. Because the data set is too big to put on the GPU. Actually, it's not too big to put on the GPU. But if you have a big data set, it's usually too big to put on the GPU because the GPU has limited memory. And so what you do is you load batches of data, and for each batch of data, the neural network updates its parameters during learning. So what I'm doing here in this data set is I'm defining a class called SSTPred, which is a generator object. It loads the data set, and then it has these two methods, length, which is the number of batches in the data set, and getItem. And getItem returns a batch of data, basically a stack of inputs into the neural network and the target output for those inputs. So it's kind of a messy engineering project to set this up. But once you have your data generator, it might take a couple hours to write that code and get it working. It's unhappy. Did anybody else get this running? I'm going to go back to CPU. Okay, so it's happy with the CPU, but for some reason it's unhappy with the GPU runtime. I really don't know why. But if anybody figures it out, please let me know. Okay, so this code here is the model definition. Like Katie's, this is a Keras model. It's a deep neural network with many different types of layers. There's lots to play with here in designing a neural network architecture. There's a whole research area called neural architecture search, where you optimize neural architectures. For many projects, it really doesn't matter what architecture you're using for a neural network. The whole point of a machine learning model is that it figures things out on its own, so it doesn't always matter. But here's a printout of the network structure, and it tells you here that it has 35,000 parameters. Questions? Okay. So here's where the learning occurs. So my model is a Keras object, and I'm calling fit, and I'm passing it the data set. And I'm telling it to only train for 10 steps for each epoch. And then after every 10 steps, it calculates the validation loss for 5 steps. So comment out these lines if you really want to train it on the full data set. I'm just doing this to be fast. But even so, you can see the loss trending down, even though it's a little noisy. And your curves will be much smoother if you train for the full number of epochs, or the full number of steps per epoch. One epoch refers to one pass through the training data. Questions? Anybody having trouble getting this working that's trying to follow along? So I've included here, after you've trained the model, the things you want to do with that are evaluate it on your validation or test set. So I've included code to actually write out the predictions here. But the cool thing that we want to do is to visualize the predictions. So I've included some code to plot the predictions here at different time steps. And here, I'm plotting for a couple random time steps the input to the model, or the most recent input, the target output, which is the next month, and the prediction of the model. So the input to the model is actually a stack of t, t-1, t-2. I think there's 3 or 4 input time steps. And then the target is the next month. And hopefully the predictions look like this target. And what I've included here is the persistence MSE, which is the error you get if you just copy the input over and make that your prediction. So if you assume next month's temperature is going to be the same as this month, that's a very common and reasonable prediction to make. It's a really dumb prediction, but you can. Our model should be doing better than that if we're going to spend all our time building a model, right? So you should be comparing the persistence mean squared error to the mean squared error of the model. And the model does do a little better, even though we've only trained for 1 minute. So there's a couple things to observe. There's a tendency for these statistical models to regress towards the mean. And so these predictions that you see tend to be a little blurry. It tends to, when it's uncertain about what the temperature is going to be, it predicts an average of the possible values, right? So you tend to end up with very blurry predictions when you're predicting images from neural networks. There's some ways to get around that. If you want nice, crisp images, you can use something like a generative adversarial network, which will make all the images sharper. But that's not necessarily good for science applications where it really depends on the application you want. So there's lots of people running ahead with these methods which give you nice, crisp images, but they're not necessarily relevant for the task. But let's see, so what error am I using? So I'm using the mean squared error. So one easy way to make the model more crisp is to use the mean absolute error instead of the mean squared error. And in that situation, you will end up with predictions that are, you get penalized less for having extreme values, and so that your model regresses less towards the mean. It tends to predict the median value at each pixel instead of the mean. And so I'm making a prediction right now that this should be a less blurry output image. We'll see. Okay. I don't know if there's much difference. I think there's a difference. You end up with more extreme values like blacker blacks and yellower yellows. Yeah. Questions. I can fiddle with the parameters a little bit more or explain some of these things, but that's the high level view. Any questions on Zoom? Yeah, so the difference between the first part and the second part. The first part was a particular location. So it was a time series for a particular location. And it was still a forecasting problem. So we're taking in previous time steps and predicting the next time step. In this problem, we're not just taking in a single location, we have the entire globe. So I think it's 56 by 128 pixels. But we are doing the same thing. We're predicting sea surface temperature for a future time step. So, the model is very similar, but in this model, we're using convolution layers. A convolution layer takes in an image with multiple channels. So typically, the images have a red, green, and blue channel at each pixel, but here, our channels are time steps. So, the current time step, t-1, t-3, t-4, those are the RGB channels that go into the model.
So why does the input layer have 4 dimensions?
Good question. So the input, so the input to the neural network is a tensor with 4 dimensions. And I just said there's 2 spatial dimensions and 1 channel dimension, which typically is red, green, blue channel for an image, but we're using that as our time dimension. The 4th dimension is the batch size. So when we train a neural network, we usually don't update the weights based on 1 input at a time. We batch the inputs together to take advantage of parallelism. So the first dimension in these neural networks frameworks is always the batch dimension, where we have a batch of, let's see, what batch size am I using? So I'm using 4, which is a very small batch size. I think the reason for this was I was running out of GPU memory when I was training this. So it takes 4 totally separate inputs. Yeah, so it's 4 different training examples. I run those through the network, compute the error, and then back propagate the gradients all in one step. That makes training faster. So that, you know, well, so when you train these neural networks, you're always limited by computation, and so you do a bunch of tweaks to make training more efficient. And batch size is one of the things where you have to do a computational trade-off. You want a large batch size so that the weights, every weight update is in the right direction. But if you have to wait too long, you decrease the batch size so that you have a faster update. These other parameters are the number of layers in the neural network, the number of hidden units or feature maps. The kernel size is the connectivity of each one of these convolution neurons, like how many neurons in the previous layer is each neuron connected to. And then this model summary is actually a pretty great way of getting an intuition for what the data looks like as it moves through this processing pipeline. So the input, again, it's a 4-dimensional tensor. This none dimension is the batch size. So in our case, this is 4. It's none because it's not set. You could actually feed it a batch size of 100 and it'd be fine. These are the 2 spatial dimensions, 34 latitude and 140 longitude. And 4 is not the batch size. This is the number of time steps that are being fed into the model for each example. So the first convolution layer is a linear mapping. Well, yes, it is a linear mapping of the input data into a new space. This new space is actually higher dimensional. So it's 32 by 138 by 30. So that this is a re-representation of the initial data. And each layer is another re-representation of the data. And in this column, the parameter number, this is the number of tunable parameters in the model. And all these parameters get updated every time you do this iterative learning algorithm. And then the output is 22 by 128 by 6. The 6 is, we're actually predicting 6 time steps in advance. So we're predicting the next month, but also the 2 months in advance, 3 months in advance, 4 months in advance. And actually in the paper, we kind of show how the performance drops off with when you're predicting farther and farther in advance. Let's see. Yeah, so here we show that if you make the prediction in January, the predictions for February are pretty good. This is the accuracy score, and it starts to drop off And the comparison here, I think, oh, so the black line is persistence, how good the persistence model is, and the green line is our convolution neural network. Similarly, this is the RMSE. Yeah. Other questions? Oh, so yeah, good question. LSTM versus a CNN. So we could have used an LSTM model in this application, just like Katie was using an LSTM model to account for the time series. We could have used an LSTM to account for our time series. The reason I didn't do that was because the input data is so large in the spatial dimensions that in order to use 30 previous time steps, that would have been a little bit overkill. It would have made training really slow and difficult. We also have less training data, and so overfitting would have been more of a problem. So instead, we're just using the last 6 inputs. And so it's equivalent to doing convolution in the time dimension as well. Like we could have done a 3D convolution model and it would have been the same as this. The LSTM model allows you to deal with a variable number of inputs. So it's very good for time series where you might have variable length time series input. But we didn't bother with that in this model. And in some sense, this is simpler than the LSTM model. Other questions? Oh, this is a good question. No, these are good questions. So if you have say you have a bunch of different variables, sea surface temperature, wind speed, etc. Would you use an LSTM or a CNN? So in the paper, we actually used wind speed as one of the other variables. I removed it for this tutorial just to keep things simple. But the way we included wind speed information was to include those as additional channels in the input. So actually, if you look at the code for the data set, well, the code's a little messy, but if you include some wind speed variables in these input names, the data set will actually return the wind vectors, both the U and the V portion of the wind speed, and you can include those as inputs to the model. It'll actually do it automatically with this code. And so instead of 4 input channels, you'll have 12 input channels to the first layer. You can think of those different variables as the color channels of an image. All right, guys. that's all I have. So I'm happy to stick around and answer questions if anybody is running things and runs into issues or has trouble. But thanks for attending.